Lead rope solo, LRS, or solo lead climbing is increasingly developing into a distinct discipline within the climbing sports. Dozens of tutorials, reports, guides and videos are circulating on the internet. In a risk assessment, EDELRID wants to explore how this discipline differs from traditional roped climbing. Hi, I'm Daniel from the EDELRID Knowledge Base, and in the following article I will conduct a risk analysis for lead rope solo climbing, and in this analysis I will follow international standards for risk assessment. First, I will highlight the technical differences between the traditional team lead climbing and the LRS, and then investigate these differences for potential additional risks. In the second step, I will assess the additional risks and present possible countermeasures or risk reduction strategies. In the third step, the effectiveness of the reduction measures will be evaluated and the residual risk will be identified. To evaluate the situation in a lead rope system, I will first explain the current code of practice. The rope is getting attached to an anchor point or the belay stance. The belay device is clipped into the rope and attached to the climber's harness. The other end of the rope is used as a final backup and is attached to the climber's harness as well. One or more cache loops are created before the belay device to help pull the rope through the device more efficiently. While climbing, the climber manually feeds the rope through the belay device or moves to feed the rope. In the event of a fall, it is hoped that the impulse is sufficient to activate the device camming mechanism to stop the fall. The first and most obvious difference from traditional team lead climbing is the fact that in LRS climbing, the climber is usually alone on the rock or on the route. The lack of a rescue solution in the rescue chain results in a risk that is significantly lower in team rope climbing. Unlike in team rope climbing, the rope in LRS is not attached to the climber, but to an anchor point or a belay station. The belay device must be attached to the harness in such a way that unfavorable loads on the carabiner are excluded under all circumstances, as the forces can be greater than in traditional belaying and the climber cannot monitor the device's position all the time. In case of a fall near the anchor, there is only a little amount of rope in the system and the impact force can be very high due to the lack of the belayer's body dynamics. The belay device, which is usually operated by the belayer with hopefully 100% attention, must now perform its jobs independently. Lastly, there is an additional risk that, due to the weight of the rope, unnoticed excess rope may be pulled into the system, creating a loop at the anchor and, in the event of a fall, resulting in unexpectedly large fall potential. So, in addition to the known risk of team lead climbing, the following risks must be named for LRS. Being alone, lack of rescue solution and rescue chain, attaching the rope to the anchor point, attaching the belay device to the harness, function of the belay device, the high impact forces, and the rope backfeed. When considering the risks and possible reduction measures, I will start from the back with rope backfeed. From about 20 meters of vertical distance from the anchor, the rope weight in the system begins to pull additional rope through the belay device. This can form a rope loop at the anchor, which can be several meters large. If there is no visual contact with the anchor or the climber isn't paying attention, the potential fall distance is increased by the amount of rope. If the climber is above a ledge or in steppe terrain, this additional rope can cause a collision with an obstacle or at least an unplanned long fall in the event of a fall. Fractures of extremities, ligament and tendon injuries, or more severe injuries can be the result. The rope slack can also cause the rope to deviate from its intended path and catch on a sharp structure. In the event of a fall, this can lead to rope damage up to the point of breaking, resulting in a potential fatal fall. Without appropriate countermeasures, the likelihood of a rope loop forming is very high. Therefore, the probability of occurrence and the extent of damage are significant, making this risk very high. However, there are several measures to prevent rope backfeed. For example, the rope can be fixed in the intermediate protections with a cloth hitch or an Italian hitch. The advantage is you don't need any additional equipment. The disadvantage, using a cloth hitch can increase the impact forces. Alternatively, The rope can be prevented from backfeeding using an elastic prusik. The advantage is you can be self-made and it's quite reliable. The disadvantage is it's complicated to attach it with one hand. It takes some time. Elastic loops pulled over the carabiners and then onto the rope after clipping also prevent backfeeding. The advantage, it's easy to use, it's small and light and can be self-tied. The disadvantage is they do not hold the rope infinitely strong. Wind or excessive rope weight can overcome the clamping effect. Some small retailers offer special carabiner inserts for sale online. The advantage is they're very easy to use and reliable. The disadvantage is they must be bought or you have to print them at home. All these measures are highly effective. When used correctly, the probability of a rope loop forming can be reduced to zero. Therefore, the risk with the use of reduction measures is very low. The high impact forces. In a partner belaying system, the belay device is usually attached to the belayer's harness. In the event of a fall, many components of the belay chain absorb part of the fall energy. The rope stretches, the rope runs through the system, friction on carabiners on all surfaces convert energy into heat. The harnesses compress and the bodies of the individuals convert energy into deformation. A significant factor is the acceleration of the belayer towards the fall load. In an LRS system, the end of the rope is attached to an anchor point and the rope runs through the belay device that is fixed on the climber's harness. Thus, a significant energy absorbing element, the belayer's acceleration, is missing in the system. The higher up in the pitch the LRS climber falls, the more rope is in the system. The smaller the fall factor is fall height divided by the length of the rope paid out, and the more energy the rope can absorb. With 25 meter or more rope in the system, even a longer fall of several meters feels hardly different from a typical hard sports climbing fall. Near the anchor, however, and especially before clipping the first intermediate protection in a multi-pitch route, the fall factor is very high, the rope can absorb only little energy, and the fall will be very hard. In unfavorable fall positions like sideways or backwards head first, an impact force from about 4 kN, depending on the climber's weight, can cause several internal injuries and spinal injuries. Near the anchor, the probability of this effect must be set to 100%. Therefore, the risk is initially assessed as extremely high. We have conducted several tests where the distance to the anchor, the amount of the rope in the system, the belaying method and the belay devices were varied. As expected, the impact forces were very high with little rope in the system, low friction situations without redirections in the intermediate protections, and a semi-automatical belay device without rope feed. With 10 meters of rope, 6 meters of free fall and an 80 kilogram person, and the rope fixed at both the anchor and the climber, we measured impact forces of just under 4 kN on the falling person. In the worst case scenario, the factor 2 fall into the anchor, however, a frequent additional effect occurs. Many of the semi-automatical belay devices used for LRS today have what feels like a blocking function. In the force range of everyday loads, this consideration is correct. In the force ranges that occur during a described factor 2 fall, however, most devices allow rope to slip through the device. The slippage value depends on the device, the rope diameter, and the rope condition, and cannot be generalized. With different ropes, we have conducted tests with a pinch and measured slippage values between 3.5 and 6 kN. These forces would immediately act on the falling person's body in a real scenario and could cause injuries due to the high acceleration, depending on the fall position and the body tension. The risk is therefore still considered high. A possible reduction measure for this problem is the use of so-called shock absorber slings, the screamers. To maintain a fully functional belay chain, the use of screamers with a residual braking strength of 22 kN is required. Initially, a first screamer can be placed between the end of the rope and the anchor point. Even in the factor 2 fall, this shock-absorbing device could convert a large portion of the fall energy and reduce the force in the system to the tier value of the device. Placing a screamer in intermediate protections also reduces the impact forces and the force acting on the intermediate protection, thus reducing the likelihood of insecure intermediate protection failing. Later in the pitch, screamers can be omitted as there is now enough rope in the system to absorb the energy. Depending on how many screamers are used and what their tier values are, the force in the event of a fall can be reduced to an extent similar to that of a normal sports climbing fall. Therefore, the remaining residual risk is comparable to that of a normal to hard sports climbing fall. Risk number 5, the function of the belay device. The issue with belay devices can be explained by the following circumstance. Typically, belay devices certified according to the European standard 15151/1 are used for LRS today. These devices are usually referred to as semi-automatic devices on the market. However, the title of the standard is braking devices with manually assisted locking. So yes, the device can block or lock the rope, but this requires a manual assistance. In the usual partner belay process, this corresponds to the braking hand. The brake hand holds the rope and thus activates the locking mechanism in the device. In the passive test of the standard, where the device is attached to a fixed point and a fall mass falls directly into the device in a 2 meter factor 2 fall, this activation is simulated by the 2 meters of rope weight on the brake side. Additionally, in this scenario, the impulse on the device is quite high and the locking mechanism is quickly activated by the static friction of the rope on the camming mechanism. In an LRS setup, often all those 3 favorable factors are missing. There is no brake hand on the rope. Falls can occur directly or shortly after clipping the bolt high up, resulting in a very low impulse on the device. Therefore, the rope can run through the device, static friction transitions to sliding friction, and the mechanism is not activated. And finally, the weight of the rope on the brake side is missing because the cash loop contains the brake rope and this moves downward with the falling person due to gravity, so it is weightless at the moment of the fall. Additionally, the devices are often modified by users to better secure the device and facilitate rope feeding. At this point, the manufacturer of the devices are no longer liable for accidents resulting from device malfunctions. All manufacturers of these devices explicitly require the brake hand principle in their instruction, which cannot be met in the LRS. Moreover, manufacturers exclude liability for unauthorized structural modifications to their devices. We have conducted a series of tests on the use of braking devices according to EN 15151/1 in LRS, demonstrating that in the worst case scenario, near the last anchor or immediately after clipping the bolt, with a medium-sized cash loop of about 1 to 3 meters of rope, the entire length of the cash loop is typically pulled into the device until the minimal resistance of the cash loop attachment provides the necessary resistance to activate the camming mechanism. Specifically near the anchor, where the impulse on the braking rope on the device is low, one must expect a fall distance up to the end of the cash loop. A collision or impact due to the increased fall distance is conceivable, and the risk of associated injuries remains high. Risk number 4. Attaching the belay device to the harness. Both in team climbing and in LRS, the belay device must be attached to the harness. So what is the difference? In team climbing, the belay device is attached to the belayer's harness. Even in long and hard falls, typically less than 2/3 of the force that is applied to the falling person reaches the belayer due to the friction in the belay chain. In LRS, the force is directly on the device attached to the falling person's harness. The forces can therefore be significantly higher. Even in hard fall scenarios, forces between 2 and 3 kN are standard on the belayer. In a hard LRS scenario, depending on the fall factor and the device's slip value, forces around 6 kN are conceivable. So where is the problem? The carabiners used to attach the device to the harness can be unfavorably loaded. The most obvious unfavorable load would be the lateral loading, and the European standard for carabiners requires a residual strength of at least 7 kN for this load direction, a value that is close to the force that can actually occur here. Even more critical are lever loads if the device is unfavorably positioned on the carabiner's locking mechanism. In a team climbing scenario, the belayer can monitor, detect, and counteract this during belaying. In LRS, the person is usually 100% focused on climbing, and an unfavorable carabiner load could lead to complete system failure, resulting into a fall to the end of the rope. The risk is considered very high unless the device attachment to the harness can withstand all possible loads. Effective countermeasures are therefore all measures that ensure the device cannot detach from the harness. This can mean using a connector that provides sufficient strength even in all unfavorable situations, such as carabiners certified according to the American ANSI standard. This standard requires sufficiently high strength even under lateral and unfavorable gate loads. Alternatively, and significantly lighter, is a Major Pete or quick link with a positioning and locking element, or, as possible with a pinch, a direct attachment of the device to the harness with additional backup by a gear carabiner, completely eliminating the risk component of the carabiner. Risk number 3. Attaching the rope to the anchor point. In team climbing, the rope ends are tied to the climber's harnesses, creating a textile-to-textile connection. Unfavorable loads, self-unclipping, lateral loads are generally excluded. Attaching the rope to a fixed anchor point usually requires the use of carabiners or other metallic components. As with device attachment, unfavorable loads can occur here. A typical and perhaps the most unfavorable load case is a locking carabiner in a rigid bolt hanger. If the rope loosens, the carabiner can tilt sideways in the hanger. Upon reloading, the carabiner gate can press against the upper bar of the hanger, and the gate locking mechanism can be broken by loads as low as body weight, causing the carabiner to unclip. A potentially fatal fall would be the inevitable result. The risk is therefore considered very high. Possible countermeasures are all setups that make detaching the rope from the anchor point impossible. Examples of such attachments include directly tying the rope into the anchor point and all types of pure soft links. This is in any case the safest attachment with reliable anchor points with sufficient eye radius. With bolt hangers, the small radius of the hanger can mean lower strength of the directly tied-in rope. The reduced strength, however, is still significantly greater than the strength of an unfavorably loaded carabiner. Rope damage from hard falls can be reduced by interposing a 3- or 4-fold looped 120 cm sling. As with device attachment, a Major Pete with a positioning and locking element is an adequate means for rope attachment. The same applies to ANSI certified carabiners, although they are often significantly heavier. A safe binder or locking carabiner with positioning device does not provide any safety gain here, as the stamping load on the gate can occur equally. With multiple anchors, a cold redundancy, for example an unloaded series connections, using the previously described attachment solution is recommended. If available, sufficiently thick and healthy trees directly tied with the rope also provide a safe rope attachment. Risk number 2. The lack of rescue solution and rescue chain. If the leading person in a team is incapacitated and hanging in the rope, they can usually be lowered to the ground or back to the anchor by the belayer. In more complex situations in multi-pitch routes, improvised rescue procedures are available. In almost all cases, the team partner is at least able to initiate an external professional rescue chain. A person who, for example, injures both hands in a collision during an LRS fall and can no longer rappel down by themselves, will require a non-trivial rescue procedure even in the protected environment of a climbing gym. Whether these rescue procedures and people capable of performing them are always available is at least questionable and should be thought out and planned in advance. And last but not least, our biggest risk is being alone. Less related to LRS in particular, but more to being alone in general. Accidents, incidents, and injuries that would not pose a fatal risk to a climbing team can be critically assessed for a single person. Direct and continuous visual monitoring by a second person would be expected minimum level of residual safety. This can significantly shorten the time to rescue in any case, even if the rescue procedure often remains incomparably more complex. However, direct visual monitoring contradicts the intention of solo climbing and will probably be rarely consciously organized. Alternatively, control calls or messages are conceivable. If there is no response within 30 minutes, the monitoring person will call for rescue in any case. This approach also does not provide an adequate solution. No one wants to worry about getting to the phone on time every 30 minutes while solo climbing. 30 minutes can be too long in a serious emergency, and the rescue could often be mistakenly called without reason. Crash sensors with emergency call function, as they are already widely available in the biking sector, could at least provide a minimal safety reserve. Being alone and the associated lack of a rescue solution poses the greatest risk in practicing a high-risk activity, and acceptable and meaningful reduction measures for this problem are by far the most challenging to implement. Sport climbing is a relatively low-risk sport when performed sensibly by experienced users. Multi-pitch climbing, alpine climbing, and mountaineering involve significantly greater and sometimes unpredictable residual risks, even for experienced users. Lead rope solo, especially in multi-pitch routes, increases the risk by several additional components that can be reduced by experience or the right countermeasures, but cannot be entirely eliminated. The fact that few LRS accidents are known today can be attributed to this discipline being practiced by a relatively small user group, often in very easy routes with low fall potential, or the users are absolute professionals who have approached their subject very slowly and carefully, and who have meticulously tested and perfected their systems.